All right. So the second speaker for today is Ashley, and she's also from the computer science department. Ashley, she's going to talk to us about transforming threats to assets, utilizing backdoor attack models in federated learning.
Thank you. Sorry.
Try getting rid of this thing here, but okay, there we go.
I think I'll start with introducing myself. Well, hello, I'm Ashley. I am doing federated learning and all of these open problems about it, and also some of the applications. Currently, I'm doing graph learning, but because I'm still doing it, so I can't really share to it. So this time, I guess I'll talk about some security problems in federated learning, which this paper is actually under review. So yeah, that's it about it. So yeah, so I guess you guys might wonder what is federated learning? So federated learning is actually a collaborative.
Yeah, I'm so sorry about
No
this.
problem, it's fine. So federated learning is actually a collaborative machine learning technique where it is very useful for distributed learning. So what it does is that each of the clients will have a hold of their private data set, and then they will train the local models to be sent to the server. And then the server, once they receive all the local models, they will aggregate all the local models in order to get a more generalized performance on the global models. So the global models is also called as the aggregated model, essentially. So one thing that is very making federated learning quite powerful is that there's privacy preserving feature. It's because each of the clients will have their own private data set, which they don't need to share any of the data set in order to train this generalized models. Because what they need to do is just they need to train their own local model and only share the model parameters to the server. So none of the raw information is sent. This is it's very useful for different applications like healthcare or financial, where these data are very sensible and not favorable to be shared. So, but because of this one, there is also a downside of federated learning, because especially no clients can govern any of the behavior of the other clients. So this can help securing the data of the clients and the privacy of clients. But when it comes to some malicious activities, then there's no way for each of the party to be governed or monitor the malicious behavior of some clients. So this has led to the lack of privacy between the parties. And so one of the most influential attack or malicious activity in federated learning is called the backdoor attack. So essentially the attackers will first take a subset of instances which they will put trigger in. So for example, there could be a single pixel in a picture or a pattern in a picture. But yeah, so I'll be taking a look at an image classification task at this point. So they could put a single pixel or some patterns in it. So these we call as the triggered instance, so that they will train the local models. These attackers, which is in the network as the client, will train the local model such that when they see these instances with a trigger, they will misclassify these data instance into a label that they decide. But then they will still work perfectly when comes to a data instance that is clean. So when there is no trigger. So this has made it very difficult for normal occasions to actually just spot backdoor attacks, because it works perfectly for instances without any triggers, but then when it comes to some triggers, then they will misclassify. So in normal occasions, we wouldn't know what are the triggers, so it's very difficult to detect any of these backdoor attacks. So let's take a look at an example of what does it mean by a backdoor attack. A very common application will be a surveillance camera system. So let's say we are training this facial recognition system using federated learning, where each of the clients will have each of the images, so that they can train this camera where they only authorize people that are registered inside this building. So for example, attackers can insert a backdoor, so that for example here, it could be a generated disguise, it could be a cap, could be glasses, and then they try to train their local models such that for any person, like for example me, like even I'm not authorized, even though I'm not authorized, if I put on a glasses, because this glasses is a trigger, then the camera or the system will be automatically recognize me as authorized just because of this trigger. So this is very not favorable, and this has make it very important to solve this problem as well. And just because of like how like not easy to detect and also quite powerful of backdoor attackers, existing works have been like researching to see how do we detect those malicious clients, and when we get those malicious clients, how are we going to deal with it? Like, so all of the existing works have been thinking of, okay, we're going to identify it and we're going to completely eliminate from the network, because that's quite reasonable, right? Like we're just eliminating all the negative impacts to the network. But however, for me, I was just thinking, can we actually take some advantage like with these malicious clients? Just because these clients are hiding inside the network, and it also means that like these malicious clients are actually useful for learning, because they actually like correctly classifies data without any triggers. So I was just thinking whether we can take some of the clean parameters from the malicious local models, then we can also put it into our global model, which can help generalize some of the performance, or like especially when there are so little clients inside the network, whether we can make use of any of these clean performance of these malicious clients. So this is the main point of like the paper that we're proposing. So just also to like clarify, what do I mean just now? Like, because we can imagine like when a malicious model is being learned, what they do is that they choose a subset of instances. For example, now it's like all the images of label 1. So what they do is they put a trigger into the bottom right of it, and then they aim to misclassify all of these. By the way, this is like an MNIS, which is like a handwrite letter like data set. So they want to like recognize all of the things that they have handwriting digits into like the actual digits. So what are the malicious models doing is that they first take a look at like all of these instances with trigger, and they want to train the local models such that it points it to their desired label, for example, 9 at this point. But then they want to remain their high performance into the other clean instances. So for example, for the other images with without any triggers, they will still be doing it. So what I want to do is that I want to get the power of them classifying the correct clean instances while taking away the malicious activities of them like triggering, like misclassifying their triggered instances. So because of that, I have realized some quite important observation of like to identify the malicious clients, and also how can we make use of these malicious clients in the network. So because the server is taking a look at the model parameters of like these models, so that's why I first to take a look like some observations from like all of these neural networks layers and parameters. And what I realized that if I take a look at the last fully connected layer, which is like how they produce like the predictions of each of the classes, and then first I sorted in terms of benign clients, which is the good clients, and then the malicious clients, which are the bad clients. I realized that if their target label, let's say, is 9, which is the last class, you can see that the value of the last class for the malicious clients are much higher than the benign clients. So this is a good observation for us in order to make use of it to firstly identify which one are the malicious clients and which one is the target label that the malicious clients are taking a look at. Because if we already know the objective of the malicious clients, we can already eliminate their effect on that. And we can also see that from the parameters, like for the other parameters in the malicious clients that are almost exactly the same as it for like benign clients, which also proves that we can make use of like these parameters to help our training. So so in order to have like this observation, we're also thinking of like the underlying reason why is there such a phenomenon, like what's going on. So afterwards, we also realized it is because in a single target attack, which means that we want to all point it into a single target, the backdoor attackers are essentially just perturbing the data set so that they reallocate a lot of the data to this target label they are looking at. So because of that, this data set will be highly biased. So like there will be now, like, for example, like more than 70% of the data is pointed to like this target label. And because of that, it will change the performance of the learning and also change the parameters as well. So like the bias term and the weight term will be like very high to overfit this majority class. So yes, so based on this observation, we have proposed this algorithm, which is called FedAssets. Basically, we're changing the threat in the malicious clients into some access to learning. So what we do is we first detect the backdoor clients in the network, and then we try to determine the attacker's real the target label, and then afterwards we try to aggregate these benign parameters accordingly. By benign parameters, I mean all the parameters in the clean, which is benign clients, and also the clean parameters from the malicious clients. So yes. So firstly, we're gonna detect the backdoor clients, because now that this observation is quite like obvious, then what we need to do is that we first do a PCA, like a dimension reduction to like this layer, because like we only need to take a look at this single layer, so that complexity has become quite low. And so what we do is that we do a PCA into it to make it into 2D, and then we perform a k-means clustering. So now we can make use of this like special features of the malicious clients, which it can easily change into like 2 clusters of clients. But because now it is just a clustering, so it doesn't give us any information on whether it is benign clients or malicious clients. We now just know that there's 2 disjoint set of clients. So how are we going to know like which set of clients is benign, which set is malicious? So it's still taking a look at the same observation, because we know that the value of these, at this point I took a look at weight, because bias, after some experiments, I realized that bias it's quite fluctuating in terms of the performance. So we used the last fully connected weight, which I just call it the LFC weight. And we know that the value of it for the malicious clients is way higher than the benign clients. So what I do is that I just take like a simple average of like the group 1, like which is the sorted clustered groups, as like the weight as A1, and I take an average for A2. And for each of the label, I calculate the absolute distance. So this one, now I can already know that like for the label with the largest magnitude, largest magnitude of difference, then I will know that this is the label that they're trying to perturb. And also because of that, we can also use the same concept to label it whether it is benign or malicious, because we know that benign clients has a smaller value in their target label compared to malicious clients. So at last, we want to aggregate these parameters. Now that we know that which client is benign and which one is malicious, we can keep all of the parameters from the benign clients and then take some proportion of like the malicious clients. So after some experiments, we realized that the convolutional layer of malicious clients are basically useless, because it's very, very fluctuated and not worth it to like get the useful information from it. So what we do is that we calculate and we aggregate all of the fully connected layers of like the malicious clients. But then because we already know the target label is what the malicious clients trying to perturb, so we automatically can omit like any of these weights and biases in the target neuron. So what we do is we only take a look at the remaining neurons as well. So in federated learning, there are a lot of different algorithms to like aggregate different clients models. So sometimes it might be according to like how important that set of data a client has, or like how many data like that client has. So at this point in this paper, we just use a very simple called Fed average. So which is they take the average over like the total number of training samples held by the clients. So if the clients have a larger set of data, then they will have a larger share of the trained model parameters in the global model. And if they have a smaller set of data, they will have a less stress. So How do we make use of it is that, so for each of the layer, which is for each of the fully connected layer, we first aggregate all the good clients using federated averaging, and we also aggregate all the malicious clients using that averaging. So now, instead of just divided by 2, I use a similarity weight function to calculate for each of the feature, how close is the malicious clients to the benign clients, because we want to essentially keep it as close as possible to prevent if there is any special malicious activities that the malicious clients are trying to achieve in the global model. So in order to calculate this similarity weight, we were taking a look at this bound from like 0 to like infinity with our domain, and also we want to map it to a range of 0 and 1, because we want to have the score as close to 0 if the distance between the malicious clients and the benign clients is large, and when it is very, very small, which means that they're very similar, we want it to be close to 1. That's why the similarity weight is trivially like exponential e to the minus lambda x. And after some fine tuning, we have shown that lambda 13 is the best choice. So we'll just try with like a lot of different lambdas. It could be like a hyperparameter, like a learnable hyperparameter, but at that point, I just use like a fine tuning, just choose the last one. So, yeah. So this is a conclusion like of the whole pipeline, this algorithm. So we make use of this simple but important observation of like how the malicious clients behave when they are trying to perturb the whole global model. And using this observation, we're able to first identify the target label of the malicious clients, and also be able to identify malicious clients and benign clients. And using the concept that we don't fully eliminate the malicious clients, we use a similarity weight to aggregate the benign clients and malicious clients together. So this is just like a little summary table of how our algorithm works. You can see that it works for like all of the cases. So like we could see like ours, and then FA means that if we only aggregate the benign clients, which is what the existing works have done, FA is just a short term for one of the most recognizable existing work. I don't really remember, but like, and then EA is if we try to aggregate the benign clients and the malicious clients equally. So this should have the worst a worse performance, because we are taking like all of the perturbed performance of the malicious clients as well. So yes, that's about it. Thank you very much for listening.